This NASA invention will change rocket launch forever. This is an entirely new launch system being tested by NASA, and it plans to slingshot payloads into space. You thought SpaceX rockets were groundbreaking, but this takes things to new heights, literally. This novel technology is called Spinlaunch, which instead of using propulsion like conventional rockets, utilizes centrifugal forces to slingshot a spacecraft into outer orbit, and can do so at only a fraction of the cost of a traditional space launch. But is it as good as it sounds? If so, what other applications could this prove useful in? Let's investigate. Born from the brilliant mind of Jonathan Yaney, a seasoned aerospace entrepreneur hailing from California, this groundbreaking technology has been quietly brewing since 2014, with the backing of industry giants like Google and Airbus. Now under contract with NASA, this visionary project is poised to redefine the boundaries of human ingenuity and exploration. At its core, the concept behind Spinlaunch appears elegantly simple. Propel an object along a circular track at breathtaking speeds before sending it soaring into the sky. However, the real challenge emerges when attempting to reach the staggering velocities necessary to catapult a substantial payload into the cosmos. To break free from the Earth's gravitational pull, an object must be launched from the ground at a staggering 40,000 kilometers per hour, about 32 times the speed of sound. Enter the impressive 308-foot Spinlaunch facility, towering like the Statue of Liberty. Currently, its launcher can reach speeds of up to 8,000 kilometers per hour, and at the heart of this technology lies the kinetic launcher. One end of this ingenious mechanism is fitted with the aerodynamic craft carrying the payload, while a counterweight balances the other end. To minimize resistance, the air within the chamber is evacuated, creating a vacuum. As the spinning process initiates, the craft and counterweight accelerate in a mesmerizing dance, their angular velocity intensifying with each turn. Once the ideal speed is reached, the craft is catapulted into the heavens, forever changing our approach to space travel. Or does it? Once the craft is high enough, it must use its own propulsion system to make the rest of the journey out to space. However, even this scaled-down prototype manages to reduce the cost of space launches to $500,000. For comparison, the price of a launch done through SpaceX's flagship rocket, the Falcon 9, is nearly $100 million. In other words, Spinlaunch can potentially reduce launch costs by a factor of 200. Currently in its testing phase, Spinlaunch sets its sights on launching its first orbital payload by 2025. And as the technology evolves and gives rise to a colossal full-scale kinetic accelerator, the costs are expected to plummet even further. Presently, the fuel consumed during the craft's second launch phase constitutes the bulk of expenses. However, if the accelerator alone can achieve escape velocity without additional fuel, its founder envisions that spaceflight, which was once the domain of only powerful nations, could become accessible to even the common man. A revolutionary design. Sure, the concept sounds promising, but is it really all it's hyped up to be? As you increase the scale of the operation, you can potentially run into a number of significant problems. For starters, there's a problem with the whole structure's integrity. When you operate a massive rotor spinning an object weighing hundreds of kilos at insane speeds, there is a high risk something might break. And if the accelerator malfunctions and the payload goes off trajectory, the launch site would instead become an unintentional artillery platform, hurling the load at super high speeds miles away and potentially endangering human settlements. At 40,000 kilometers an hour, a 200-kilogram object hitting the ground would release roughly 1.28 terajoules of energy. That's equivalent to 300 tons of TNT exploding. For comparison, the largest non-nuclear bomb in the US military arsenal is the mother of all bombs, or simply MOAB. It explodes with an energy of only 11 tons of TNT. Furthermore, it is unlikely that technology could ever be used to transport humans to space. Even if you accelerated the manned spacecraft slowly enough for a person to experience manageable G-force, the centrifugal force would still absolutely annihilate him. For example, at a speed of 40,000 kilometers per hour, a person's body would be experiencing 10 teranewtons of force pushing against it. That would be as if the entire Chrysler building was placed on top of you. Needless to say, a person spinning at such speeds would have turned into an unpleasant bloody mist. Even at a scaled-down speed of 8,000 kilometers per hour, 1,000,000 newtons are pushing against a person. That is similar to if a plus-sized blue whale landed right on top of him. A guaranteed death. And this brings us to another limitation. The objects in question must be made of materials able to withstand such incredible force. So more sensitive probes and satellite equipment are out of the question when it comes to launching them with this technology. Even at breakneck speeds of 8,000 kilometers per hour and with the help of advanced rocket propulsion, we still face challenges when it comes to launching payloads safely into space. One major constraint lies in the type of fuel we can store on board the delivery aircraft. You see, traditional liquid-based rocket fuel isn't quite cut out for the job, as it necessitates a complex network of valves, pipes, and pumps. As it stands today, we have yet to develop a system robust enough to endure the extreme accelerations and vibrations that occur during a high-intensity centrifugal launch. Instead, Spinlaunch's team and NASA aims to utilize solid propellants for their launch crafts. Now, that has some advantages, but also its fair share of drawbacks. The biggest one being it is less efficient and controllable compared to liquid fuel. It again puts limits on what kind of payloads we can launch with this technology, with objects of higher mass or sensitivity out of the question. Lastly, there's also the potential difficulty of creating a vacuum in a chamber of such a massive size, because, believe me, it takes up a lot of power. While the information on the power consumed by the Spinlaunch facility isn't publicly available, we do have one for NASA's Space Power Facility, SPF. Its vacuumed chamber at 122 foot high and 100 foot wide consumes 11 megawatts of power, equal to 1,003 suburban houses. The full-scale version of Spinlaunch is proposed to be many times bigger than this, and so likely would be consuming the energy's worth of an entire town. Of course, the technology is entirely new and still in its developmental stage, so it would be unfair to cast it down based on its current limitations. With time, the technology will improve, and workarounds could be discovered to overcome its existing technical and engineering challenges. Right now, its application is best suited for launching simple space satellites into low Earth orbit at very economical costs. However, in the future, I do believe it could be our gateway to building true megastructures in space. With launching costs significantly reduced, sending material into space in large quantities would be highly economical. Right now, the International Space Station is the largest man-made object we have in space. However, in the future with Spinlaunch, we could see the stations built in space 100 times larger for 100 times less cost. We could even create an orbital version of the Spinlaunch kinetic accelerator. It could be powered by massive solar panels and would not be limited by Earth's forces such as gravity and air resistance. Such facilities could help immensely in improving space travel. Picture this scenario. A spacecraft could be launched from its Earthbound facility into space. It could then be docked inside the orbital station, and from there be launched further into space. Multiple stations could be built in the solar system, serving as stops for traveling spacecrafts. Eventually, I can see the technology even feasibly used for taking astronauts to space. Centrifugal force could be mitigated by using a counter-rotating platform housing the passengers. Reducing G-force to acceptable safe levels is even easier, slowing down the acceleration rate of spinning. Although not all potential technology applications might be so beneficial. Let's talk again about the orbital kinetic accelerator I mentioned. Sure, it could be used to launch objects at high speed away from Earth. However, conversely, it would also be used to hurl objects at high speed towards Earth. In this scenario, you potentially have a weapon just as deadly as a nuclear warhead, minus its drawbacks like radioactive fallout. A tungsten rod 20 foot long by 3 foot wide, launched at 40,000 kilometers per hour from orbit onto the Earth's surface, would release 67.4 terajoules of energy. That is equal to 16,100 tons of TNT. This is roughly the exact yield as the atomic bomb dropped on Hiroshima during World War II. Spinlaunch absolutely has the potential to transform space travel in the future as we know it. However, it still needs more investment into R&D so it can resolve the limitation it currently faces. Once that hurdle is out of the way, the technology is bound to propel our society onto new horizons, for better or worse. Let us know your thoughts on this technology in the comment section below.